Recording. Somudha, recording.
Yeah, it has started.
Okay, can I start? So,
Yeah, please.
okay. A very warm and delightful evening to everyone. My name is Omkar, and I would like to take this privilege to welcome all of you to the Invited Talk 22 organized by Karili. I will start by giving a brief description about Karili first. Karili, as the name suggests, it is a maths club of MTT's alumni who organize regular types of online talks and seminars on different topics of mathematics. The name curry leaf is inspired by the famous curry leaf trick often used by Dr. Kumreshan Shah. Now, let's move on towards the topic of today's talk, which is about the space around knots. In mathematics, knot theory is the study of closed curves in three-dimensional spaces and their possible deformations without one part cutting through another. Knots may be regarded as formed by interlacing and looping a piece of string in any fashion and joining the ends. To a topologies actually, knots are closed curves embedded in three-dimensional spaces. It is actually useful to model them with a rope or cord and to diagram them as projection on a plane. Knot theory has a potential in basic research to create new kinds of medicines, and I think it is also within some chemotherapy drugs also. In maths itself, knot theory is helping mathematicians work out the radius of higher dimensional spaces also. So now, to enlighten us more about this topic, we have with us a distinguished speaker, a very famous mathematician, and a great personality for today's meeting. And he is none other than Dr. Sandy Melo, sir. Dr. D. Mello is a renowned expert in field of mathematics and topology, especially in topological properties of real algebraic curves and real algebraic knots also. He is also an MTTF alumni. He did his PhD from Stony Brook University in the United States. Now, he is an assistant professor of Eisner Mohali also. We're truly honored to have Dr. D. Mello with us today to share his knowledge and insights on this captivating topic, properties of the complement of a knot, especially the fundamental group of the knot complement. So, to all the viewers who are watching us through YouTube and those who are with us in this meeting are free to ask any types of questions regarding this topic by raising your hand in this meeting, or you can leave a comment in the comment section in YouTube also. So I will convey all your doubts and questions to sir. So over to you, sir.
Hi, thank you so much. Sorry, I just had some trouble. I sort of disconnected something. Just give me a few minutes. I accidentally closed my thing. So, all right, I think it's okay. So I'll just share my screen. Is my screen visible now?
Yes, yes.
Okay, thank you. Sorry for the delay. So, so my subject, of course, is about knots, but I want to sort of emphasize slightly different things than is often seen when one is reading some of the text in knot theory. It's quite typical to come across, say, the coloring invariant, and to have a lot of emphasis on the combinatorial methods of analyzing knots. And what happens is that some of these invariants that one comes across, and some of these concepts that one comes across, they tend to look a bit mysterious. And the three coloring invariant is one of them, and I'll talk about a couple of others. And that's often because the way they were discovered was very different from how they were finally presented. So it's possible to actually present both the theorem as well as the proof in a manner that has nothing to that seems to have nothing to do with the original method, but it was inspired by that, and that's how one thought about it. So anyway, let me start. So of course, what I'm looking at are knots. That is, they are things which are homeomorphic to the circle. However, they are embedded inside R3, or that is the three-dimensional space, or inside the three-dimensional sphere, S3. Usually S3 is chosen because it's compact, etc. And so, it's also convenient for other reasons, which I'll talk about a little later. So anyway, so we're looking at the, we're trying to understand, these objects. And obviously, because, they are actually within, they are, it's important to understand that we are not looking at the object alone, right? We're actually looking at the object as it is situated inside S3. So even a knot equivalence, for instance, is when you say the two knots are equivalent, you don't just demand that the two knots be homeomorphic. Rather, you demand that the two knots are, that the homeomorphism that takes one knot to the other is it is a homeomorphism that extends to the entire S3 to itself, to the entire ambient space to itself. So you look at so two knots are equivalent if and only if there's a homeomorphism from the 3 sphere to itself, which maps the first knot to another one. And one could even talk about one strengthens it a bit by demanding that this homeomorphism be isotopic to the identity. That means it's homotopic to the identity, and at each stage it should remain a homeomorphism. So anyway, since it depends on how it's situated inside inside the ambient space, we could ask questions. For instance, what is the fundamental group of the complement, for instance, right? So we look at the complement and we try to consider its fundamental group, and the fundamental group, I'm assuming that most of you know what the definition is. So you're looking at homotopic classes of loops, or paths rather, which are loops based at a particular point. So you fix a base point, and then you look at the path. You look at a loop, and as you can see over here, this loop, I can deform it. So we're looking at homotopic classes. So I'm homotopping this loop. But you can see over here that there is an obstruction to making the red loop homotopic to the green one. You see this? The red loop, I started it off over here. All these loops are representing the same homotopic class. They're representing the same element in the fundamental group. However, if I look at the green one over here, that's a completely different one. Okay, and this brings up another interesting thing about the way we draw knots. We draw knots as diagrams like this, and that involves these arcs. And if you look at these breaks in these arcs, they seem to be something which is not really of any geometric significance. After all, the fact that I could define this is a knot diagram. It's a way of representing a knot. That means in 2 dimensions. So you projected the knot, and you sort of if you project a knot, then of course you'll get these crossings over here. And if you just took an ordinary projection, they will appear as double points. They'll appear locally as 2 lines which are intersecting. In order to give some visual indication of which one is above and which one is below, which is all you need to know to recover the knot up to isotopy, you need to put this sort of break over here, right? And so it seems that break is just for a visual representation. and these arcs that it breaks up into, the diagram, the knot diagram, it breaks up into these disconnected arcs, right? You can see that these are disconnected. But that disconnected thing just seems to be, again, just for visual representation. But actually, it does have a topological significance when you look at it from the perspective of the fundamental group. And that's all because the base point is fixed. You see, because the base point is fixed, I cannot go beyond this. You see, imagine the base point is above, so I can't go beyond this. This is an obstruction. Notice that if I did not have a base point, imagine a sort of a loop over here, I could have just moved the loop along the knot and brought it anywhere. I mean, I could have moved it anywhere and it could go across. I'll come to this point later, but it's suggestive of the fact that if you replace the fundamental group by the first homology, then there's going to be no difference as such. So the base point makes all the difference. I mean, the base point is what makes the fundamental group of the knot, differ if you change the knot, possibly differ. I mean, the point is that because of the base point, so let me put it another way. If you looked at the homology where, there's no concept of a base point involved. Let's say you look at singular homology, or even if you triangulate everything and you look at it in terms of simplicial homology, then the homology of the knot complement will always be Z. It will always be the same. That point will become relevant later. But anyway, for now, let's just analyze this. So what we're defining over here is this knot group. It's called a knot group, but it is essentially the fundamental group of the complement of the knot. Okay, and of course, one could ask, this is the general question itself, what is the fundamental group? See, the fundamental group of the knot itself, since the knot is homomorphic to S1, the fundamental group of any knot is always Z. So, this is a better question to ask. What is this fundamental group of the complement of the knot? Because after all, what gives rise to knotting is the way S1 is placed in the ambient space. Anyway, so we have this knot K1, and you can see that the fundamental group of the knot is actually going to be an sending K1 to K2, but it's a homeomorphism that extends to the whole of S3. That is what is meant by equivalence. Then even when you consider the complements, right, F is going to be well defined on the complement, and you get a homeomorphism over here. And because it's a homeomorphism, the knot group, the fundamental group of the complement, is going to be the same. It's going to be isomorphic, rather. Whether you look at this one or whether you look at that one. So, all right. So we have so the knot group is an invariant under isotopy. Now, what use is that? Well, the usual explanation for that is that the moment you have an invariant, you can tell apart knots. Now, the thing is that knots are represented by diagrams. But if I give you two different diagrams, it is extremely hard to know whether or not the two diagrams represent the same knot or not. I mean, there could be different representations of the same knot. I could represent this knot, for instance, in a very complicated way. For instance, I could make a lot of twists over here and actually do things which are far more complicated and which make it look like a completely different knot. And but yet it's equivalent to this one. So, since it's hard to tell apart knots, the usual way out of this is to try and define things which are invariant. So things that, given a diagram, you can compute the invariant easily, and therefore, if you're given two different diagrams and you get a different invariant, then you know that these two diagrams represent completely different knots. They're not equivalent knots. If the invariant turns out to be the same, however, for both of them, then the question is still open, because we don't know if there's some maybe the invariant is not strong enough. Anyway, so how good is the knot group as an invariant? Well, there is a theorem which tells you that if the knot group is Z, then it must be an unknot. So an unknot looks like just a circle. Okay? So there's no knotting at all. There are no crossings in the diagram, etc. So you can represent it that way. So it's something which is isotopic to that. Of course, you can represent it with, you can have a complicated representative of an unknot. However, an unknot is a knot which has a simple enough diagram, and that diagram is a circle. So the circle is so you look at the knot, the isotopic class represented by simply the circle placed inside S3, and that is the unknot. And as I said, there's a result which says that the unknot is can be detected by the fundamental group of so if the fundamental group is so the unknot of course has fundamental group Z, the complement of that has fundamental group Z. But if you have a knot in fundamental group, the complement of the fundamental group is Z, then it is known that it will be the unknot. It's a difficult theorem to prove, but I'm stating it just to give you an idea that the unknot is this invariant is quite a powerful invariant. So the question we should ask, therefore, is how do we compute it? More importantly, how do we compute it using a diagram? Now, so in general, any group can be presented by the group presentation, which is that you give generators, so the idea is that the group is generated by some elements, and there are some relations. So formally you say that you look at the free group generated by those generators, and then you quotient out by the smallest normal subgroup containing the so-called relations. So so for instance, if you want to represent Z, direct sum Z, you would take the free group generated by two elements, and you would impose the commutative relation, so that AB, A inverse, B inverse would be the identity, and that would force A and B to commute, and it would force all the elements to commute with each other, and that would give you a Z direct sum Z. So what we would like to do is we represent knots by diagrams. So the question is, given a diagram, can we extract information about the fundamental group of the complement of the knot? And the answer is yes. And it has a rather simple way. There's a rather simple way of doing it. The proof is a bit, it's a bit tedious, but it is not. The idea behind it is extremely simple, and I'll illustrate the idea. So what you can do is, we've already seen this arc, right? When it started off over here and we moved it over here, and now I have another loop which I can move across this arc. So you can see that every time the arc ends, that is when I can no longer move the loop beyond that. So what I could, so therefore, you can see already that you can make an educated guess, and all this can be proved rigorously by using the Seifert-Van Kampen theorem, which essentially tells you how to compute fundamental groups of unions when you know the fundamental group of the individual pieces and the intersection. So anyway, so for each arc over here, I can have one generator for each arc, right? So in this case, n would be equal to 3 because I have 3 arcs and I have these generators. So here you can see that I've put in one more arc, and so the red arc will essentially, I can move it. Sorry, the red loop can be moved across this arc. The blue one can be moved across this one, and the green one can be moved across this one. So in general, you have as many arcs, as many loops, as many generators as the arcs, right? And of course, this is still an educated guess. It requires a proof as to why these generators are enough, but it's not hard. You see, so, but now let's try to examine how we can, sort of combine So, here are these two arcs. You see this, the red and the green arc. I'm going to show you how the blue arc will help us to so essentially what I'm going to show you is this, that when we conjugate the red arc with the blue one, then it will become isotopic to the green one. So I'll show this visually. So what we do is, so here's a blue arc. I'm going to put in another blue arc, which is essentially isotopic to this one, but so it represents the same element in the fundamental group, but I've separated it because it'll make the conjugation clear. So now notice that when I compose this red and sorry, there seems to be something interrupting. Are you able to see my screen?
No, we see a black screen.
Okay, something. I don't know what happened here. Something popped up and it's
Maybe you can reshare, stop the sharing and
yeah, no, there's something just happened to my, okay, yeah. All right, I'll just actually my Zoom has been giving a lot of trouble with this thing, and sorry, I'm trying to avoid doing that, but I think I'll have to just log out and log back in.
no, you
So,
can stop the sharing and then just reshare.
I'm trying to do that, but unfortunately it's not.
Okay, let me help you.
No,
I'll-
no, it's not that. I mean, I'm also seeing the black screen. So sorry, I just maybe log back into it. I think that might be a little. Otherwise, I could. Sorry, I'll just log back in, please. That might be. I don't know how long this will take. Otherwise,
Okay, all right.
Soumya, is there an issue?
Yeah, there was some problem with the sharing of the screen. Yeah.
Maybe you can pause recording.
I really hope I don't face this problem again now. I've been facing a lot of trouble with Zoom today.
Yeah.
All right, is the screen visible?
Yeah. Yes.
Right. So okay, so so you see, so what happens is that when I concatenate this blue curve, this blue loop with the red one, and then I concatenate with the inverse of it, the arrows illustrating the orientations are missing, but if I had to do that, then once I concatenate it, the point where the blue and the red arc meet, that is no longer an endpoint. And when one is looking at path homotopies in fundamental groups, all one has to all that one demands is that the endpoints remain fixed. So since this is no longer an endpoint after concatenating, we can easily dislodge it. And once we dislodge it from there, you see here, I've dislodged it from there now. And, and then it is now free to become isotopic to the green arc. So we get this relation here that, one of the generators is related with the other one via the conjugacy relation. I'm not going to the specifics of it because we don't really need it at the moment. You can look at that later. So the point is that, so let me summarize. This is just one of the relations. Of course, there are several. One for each crossing. So essentially, for each arc, you have a generator. And for each crossing, you get a relation, which is a conjugacy relation. And the fact that it's a conjugacy relation is going to be relevant for us. Okay, so now we seem to have solved the problem, right? Because we have an invariant which seems to be decent enough to tell apart the unknot from any other knot. True, it's not strong enough to tell apart any two knots, but then that's too ambitious. And nevertheless, it's decent enough to do that. And we have a way of computing it given a diagram. And so it seems like we've made a great deal of progress, except the problem is that we have only transferred the problem from knot theory to group theory. Because when I'm given, it's a known problem that supposing I've given two different group presentations, it's very, very hard to know whether they represent the same group or not, whether their presentation is the same group or not. It's very hard to tell by just the generators and the relations. It's a word problem. And so we haven't really made too much of progress in this regard, right? So what are the next thing that we can try out? Well, we could try to abelianize. Now, there is if you try to look at say when one first studies fundamental groups, and if you try to apply them to for surfaces, and you try to compute the fundamental group of surfaces, in order to prove that surfaces, say for instance, to prove that, let's take something simple. If you want to prove, say, that the torus is, say, not isomorphic to the double torus, that is the torus connected sum with itself. You could compute the fundamental groups, but then it will be hard to tell whether the way you have represented those groups, whether they are actually different groups or no. And that is because they are non-abelian, and there is no structure theorem for non-abelian. I mean, not at least not a simple thing for abelian groups. For instance, you know that you can write them as direct sums of the free part and the torsion part, and there's a theorem which tells you that there's a standard way you can write them out, and two abelian groups are isomorphic, and then only if the standard way is the same. So for abelian groups, things are a lot easier, and so you could say, well, okay, I'm going to abelianize the group. And what does that mean? It means that you force commuting relations. So the elements do not commute with each other. You force the commuting relations. Formally, that means that you are going to say that formally this can be expressed by saying that the commutator of any two elements, of any pairs of elements, should be the identity. So another way of doing this formally is to take the group and to quotient it out by the commutative subgroup. And the commutative subgroup is automatically normal, which is, it can be proved easily. So you don't need to look at the smallest normal subgroup of that, but essentially you're forcing this relation. And so you can abelianize any group. And so one might say that, look, if you're given two different non-abelian groups and you want to check whether they are, different or not, because you're given them by a presentation and you want to check whether they represent different groups or not. Well, abelianize, And when you abelianize, then you have a structure theorem which tells you that it has to be one of these standard groups, that is Z direct sum, the Z mod ni's, and with the relation there. And so you check which one it is, and then you see whether it's different or not. So let's try that over here. If you had to abelianize, what would happen is you would, of course, get the same generators, but the relations this time, well, if you abelianize, conjugacy is, well, in that case, the AK inverse can interact with AK, and that will cancel out. And so you get that AI is equal to AJ. And in a knot, what would happen is that you would find that all of these are related by conjugacy. And so all the generators, I've left out a few details, but easy to check details, but all the generators would be equal to each other. And so the abelianization is going to be generated by one single element with no relation at all. And so it is Z. So the abelianization is completely useless, actually. When we abelianize the fundamental group of the complement of a knot, no matter what the knot is, it is always Z. So it is of absolutely no use whatsoever in checking whether two knots are different or not. Well, that's the pessimistic way of looking at it. The optimistic way of looking at it is to ask, what constraints does this being equal to Z impose on the kind of groups that a knot group can be, and how can we exploit that? And that is the next part of our discussion. So you see, when there's a so here's what we can do. We can actually try to count. We can try to look at the homomorphisms into a non-abelian group. Okay, so here maybe let me state it this way, that there's a way to characterize the abelianizer of a group, and the characterization is as follows: that if you're given a group, and then its abelianizer, there is a natural map from the group to the abelianizer. That's essentially because the abelianizer is a quotient of the original group. So there's a natural map from there. And in fact, given any homomorphism from the original non-abelian group to any other abelian group, it always factors via the abelian one. So don't worry if you don't completely understand what I'm saying. It's at least addressed to those who know about this, but it factors via that. And
sorry to disturb, Dr.
Yeah.
Shane. I think
Yeah.
We'll have to again start over the meeting.
Yeah, sure.
So I think now we can just stop if you're
Right.
comfortable. Yeah. So we'll start again at 6:40. So everyone can leave the meeting now. Yeah. And